Today we're going to be talking about comparing functions. By the end of this lesson, your lesson objective is this. I can compare the components between two functions. When I say components, those are the vocabulary words we're going to talk about today. The first vocabulary word is rate of change. The rate of change and the slope mean the same thing, or how steep a line is. Okay? We have different ways of finding the rate of change or the slope. We can do that on a graph. When we look at a graph, we find 2 points and we count the rise over the run. That's how you find slope. So rise over run. That's how we find it in a graph. In an equation, we look for the coefficient, or the number right before the x. Sorry, I'm not spelling very well today already. So from a graph, it's rise over run. From an equation, we look at the coefficient. And then one more thing is the table, and sometimes that's the hardest one. The table, we choose two ordered pairs, and then we use our formula. y2 minus y1 over x2 minus x1. I wanted to remind you also that we indicate slope by the letter M. Okay, so now let's look at the next word. This is another component that we might use to compare two functions to each other. It's the y-intercept. Y-intercept is indicated by the letter B, and it is where a function crosses the y-axis. Now the intercept doesn't have a letter, but to indicate what it is, but like the y-intercept, the x-intercept is where a function crosses the x-axis. So the only way to really do this is to jump right in and try it. I'm going to give you 3 examples today, and then you're going to use what you know about slope, y-intercept, and x-intercept to do the work that we're asking you to do. So the table and the equation both represent linear functions. Remember, a linear function is a straight line. Which function has a greater rate of change? When they say the words greater rate of change, they mean the same thing as slope. So we're going to find the slope of both function A and function B, and then we're going to compare them. Which one's larger? Which one's smaller? Okay? So let's look at the equation first. The equation is the easy one because we know that in the equation, the slope or the rate of change is the coefficient. So we know for function B, the slope is -3. Let's look at the table. That's a little bit different because we have to use a formula. And I want you to remember, looking at this, that this table is sideways. So the x value is 2 and the y value is 21. So I'm going to choose 2 different ordered pairs. It doesn't matter which ones I choose. I'm going to choose these 2 right here, and I'm going to write them out. 4, 17, and 5, 15. And then I know that I have to use my formula, so I'm also going to write x1, x2, Mrs. Hall, you're losing it. y1, and then x2, y2, so that I know where to put my things in the formula. My formula is y2 minus y1, that's finding the slope, over x2 minus x1. So let's try that. 15 take away 17 over 5 take away 4. 15 take away 17 is -2. 5 take away 4 is 1. So my slope for my table is -2. All right, so let's compare them. Function A has a slope or a rate of change of -2, and function B has a slope of -3. -2 is greater than -3. So function A has a greater rate of change than function B. Here's another example. Marcus graphed the function shown. Anna wrote the function given by the equation y equals 4x minus 2. Which function has a greater y-intercept? Well, let's find that out. We're looking for the y-intercept. Let's go to the equation first. I think that one's the easiest one to find. In the equation, we know that the y-intercept is the constant. So the y-intercept for Anna's function is -2. Let's go over to Marcus's function and look at his graph. We know that y-intercept means that's where it crosses the y-axis. Okay, so Marcus's y-intercept is -4. Now let's compare them. Marcus's is -4, Anna's is -2. So here's what we know. Anna has a greater y-intercept than Marcus. We're not going too deep in depth, we're just comparing the two. All right, Sean and Mel leave an amusement park at the same time. Both drive home at a constant speed. The table shows the function that models Sean's trip home. The graph shows the function that models Mel's trip home. Who gets home first? Well, when we're looking at this, let's look at the graph first. Mel's distance from home in miles is on the y-axis, and the time in hours spent driving is on the x-axis. What we're looking for is how many hours it took Mel to get to her destination, which is home. So we're looking for the x-axis, or the x-intercept, because at 0 miles from home, that means we're there at our destination. And we can figure out, we can look where the x-intercept the line crosses the x-axis, tells us how many hours it took us to get to that 0 distance, okay? So the x-intercept for Mel is 4 hours. It took her 4 hours to get home. Now let's look at the table. The time spent driving is x, the distance from home is y. Remember, we're looking for the y to be 0 because that means we're at home at our destination. So when Sean is actually at home, it took him 5 hours to get there. So Sean's x-intercept is 5 hours. So the question asked was, who gets home first? Well, it took Sean 5 hours to get home, and it took Mel 4 hours to get home, so Mel gets home first. I think the only way to really do this and to get good at it is to make sure that you're reading through the example, you're looking at what information you're trying to compare or find, and then you use all the knowledge you have of slope, y-intercept, and x-intercept to answer the question. Write down anything you might want to ask, and we will work on this some more tomorrow.